Let's consider a situation. A conducting loop is placed in the magnetic field and keeps stationary. The magnetic field is out of phase. The magnitude of the field is increasing with time. According to Faraday's law, the current is induced in the loop due to the changing magnetic flux through the loop. Please recall what we learned in electricity. A current is produced due to the net motion of the charge carriers under the action of the electric force exerted by the field. Hence, a current is related to an electric field. In the same manner, we have an induced current in the conducting loop, meaning an electric field is created in the conductor as a result of the changing magnetic flux. Now, we replace the conducting loop by a plastic loop. All other conditions keep the same. What happens? No current, but the EMF is induced because of the changing magnetic flux through the area of the loop. Based on the definition of the EMF, we have this expression. Epsilon equals the line integral of a non-electrostatic field over the closed path. By applying Faraday's law, the induced EMF is the negative of derivative of phi b with respect to time. Combining these two equations, we have this one, which is the general form of Faraday's law of induction. Please note, here E is the induced field. Therefore, if the magnetic field is changing with time, the electric field is induced no matter there is a loop or not. Just like the electrostatic field, which is independent on the presence of the test charge, a changing magnetic field could generate an electric field in empty space. From this expression, you may notice that the closed line integral of the induced electric field is obviously not zero. This is totally different from the electrostatic case. In our study of electricity, we have seen that the electric potential difference between any 2 points A and B in electric field E can be written as this one. If the electric field is conservative, the line integral is path independent, which implies the line integral of the electric field over the closed path must be zero. This is the case of the electrostatics. But here, this expression indicates that a changing magnetic flux will induce a non-conservative electric field. Therefore, we must distinguish between the induced non-conservative electric field resulting from the changing magnetic field and the conservative electric field which is produced by the stationary electric charges. As an easy case, let's consider a uniform magnetic field which points into the page and is confined to a circular region with radius r as shown in the figure. Suppose the magnitude of B increases with time. Let's find the induced electric field everywhere due to the changing magnetic field. Due to the symmetry of the situation, we choose the integration path to be a circle of radius r. The induced field has the same value at each point on the circle. According to Lenz's law, the induced current must flow counterclockwise to produce more outward flux to oppose the increase of the original flux. Correspondingly, the direction of the induced electric field is shown here. In the region r smaller than the uppercase R, the rate of change of magnetic flux is this one. Here, A is the area of the closed loop we choose. By applying Faraday's law, we have this one and solve for E. Similarly, for the region R larger than the uppercase R, the induced electric field is obtained by this one. But please note that A is the area of the circular region where there is a magnetic field B, since here R is larger than radius of the circular region. This figure shows the plot of the induced electric field as a function of R. From this example, we could see that in space outside the region of magnetic field could also experience an induced electric field. We discussed the motional EMF produced by the motion of the conductor in the field and also explored the induced electric field. In the next lecture, I will show you an important application of electromagnetic induction, generator.